Thank you for the introduction, and thank you all for being here. I'm going to talk about algorithms and lower bounds for convex optimization using quantum oracles. This is actually a joint talk about two papers, one from a group at CWI and one from a group at the University of Maryland, with this giant author list. I'm just going to quickly do this. Quickly going to split this up. The first paper is Quantum Algorithms and Lower Bounds for Convex Optimization by Shuvanik, Andrew, Tongyang, and Saudi. And the other one is Convex Optimization using Quantum Oracles by myself, Andrew Skillian, Sander, Ronald de Wolf. And the papers have mostly the same results, with some minor differences that I will try and make clear during the talk. So we already heard a lot this session about convex optimization, but let me recap it a bit for those who just came in. So I stole this slide from Tongyang's earlier presentation. This was about why you would want to study STPs, but I think we can just fix this by putting convex optimization there. STPs in particular are a form of convex optimization. So why would you want to do this? Well, a lot of machine learning problems involve convex optimization, a lot of algorithm design. A lot of problems in quantum information involve convex optimization. And convex optimization is a bit broader than just STPs and LPs. And we'll talk about the general setting in this talk. So in convex optimization, we're going to have a convex set, as you might expect. And we're going to say this is of dimension n. And we want to optimize some convex function over this. And this is actually all we're going to assume in this talk. So there's no additional structure. There's no constraint that the matrices are PSD or something like this. It's just a convex set, and we want a convex function over this set. And without loss of generality, we're going to actually assume that this convex function is linear. And this is really without loss of generality, because you can always, for a different function, look at the graph of the function and optimize over the graph. So I'm just going to denote the direction that we want to optimize in with this arrow here. So we want to move as most as we can to the top right. So if we don't know any structure of the problem, we actually still need to say, like, how do we have access to the instances of these problems? And we're going to assume oracle access to this set. And this was first introduced by Groucho, Lovász, and Schrijver in 1988. And they considered a bunch of different oracles. And the first and possibly simplest oracle for a convex set, I forgot. And they also assumed that whatever oracle we have, we always at least know some point in the set. And this is rather natural that you need some point in the set, because otherwise you don't even know where your set is. It could be all somewhere randomly placed in all of Rn, and well, good luck finding it. So you assume we have a point, and we actually assume that we also have a little region around this point. But this actually comes very natural. This tends to be the origin with a little ball around it in many problems. So the first oracle they considered was actually a membership oracle. We'll denote this with mem. And a membership oracle is as simple as it gets. You give it a point in the set, it says, yes, this is in the set. You give it a point outside of the set, it says, no, this is not in the set. So it just gives you one bit of information about your set every time you query it. But you could have a little bit more of a sophisticated oracle, and that could be a separation oracle, which we will denote by sep. And this does the same as a membership oracle, except that if your point is outside of the set, it's going to tell you why. It's going to give you a separating hyperplane. So this is some hyperplane that lies between the set and your point. So this already gives you a little bit more of information. Actually, this gives you an n-dimensional vector, so it gives you quite a bit more of information. And then in a little bit strange way of stating things, we actually consider optimization as an oracle as well. So for an optimization oracle, you would give it a direction, and it would tell you the optimum of the set here on the far boundary here. So of course, normally we would consider this as actually the goal that we want to solve, but we can also say, well, we would like to build an oracle for this set that gives us the optimizing point. And lastly, we're going to also consider validity as an oracle. Validity oracle does sort of a similar thing to optimization, but the only thing it does is you ask it for a direction and a possible value, and it tells you whether there is a point that reaches that value. So you can see this as well as you give it a hyperplane, and it tells you whether there's a non-empty intersection of your set with the half space that's denoted by this hyperplane. So validity with a bit of binary search you can use to find the optimal value of your problem, while optimization also gives you the optimizer, so the actual point that reaches this optimal value. And we're going to be considered in how these different oracles relate. And in particular, I have to say here that, of course, all oracles in practice actually have precision parameters and error probabilities, but we will ignore these in this talk because, well, it makes the calculations a little bit easier. So we have these 4 oracles, and we would want to consider how they relate to each other. And actually, in the first work, Grosjean-Lovas and Schrijver already they proved that all these oracles are polynomially related. And what I mean with an arrow here, the arrow going from mem to sep says that with poly n queries to a membership oracle, we can build a separation oracle. And the arrow going from sep to opt says that with poly n separation queries, we can do optimization. And n here is the dimension of the space. And it's important to note here that we always care about algorithms that work with logarithmic dependence on the error. This is different from, for example, the STP solvers we saw before, or the previous talk. We want a logarithmic dependence on the error. Then we can immediately also state that actually going from sep to mem should actually just require 1 query because separation is strictly stronger. And the same on this side. If you can find an optimizer, then you can actually also just answer the validity queries. And then in 1998 and 1989, these authors improved the middle part. They showed that actually n separating hyperplane queries suffice to optimize. However, the computational complexity involved here was quite large, and in a series of subsequent works, this was the time complexity, so this is additional to the number of queries that need to be done, was brought down to n to the power 3 a few years ago by Lissertford and Wong. And it's still open whether this can be further improved. And then finally, this final poly n, was recently in 2017 improved to n by Lissertford and Van Pala. And this is actually the result we will mostly focus on. So this tests that with n membership queries you can do separation, and this is actually tight classically. But what we will show in this talk is that this actually can be improved exponentially with a quantum computer if you have quantum access to a membership oracle. And this would also improve the best known membership to optimization algorithm from n squared to n in the quantum case. So let me quickly recap how their proof works, because we'll follow it quite tightly, and then I'll give the quantum improvements where possible. So we want to build a separation oracle using membership. So let's look at our set again. We have a point with a little ball around it, and we have this point here that's being queried, and that we want to separate from the set. So ideally, we would like to find a line like this. But we don't know this yet, so let's build one. So we're going to consider the following box that starts at our little ball and goes up to a quite small region around our point that we want to query. So this is a cylinder in Rn, or a box. And in this box, we're going to look at the boundary of our set, here drawn in red. And you can consider this boundary actually, you can consider how far the distance is between this boundary and the line here. So you can measure these distances. And you can actually then see that the boundary of the set is just a function if you look at this domain. And we call this the height function. And the nice thing about this height function is that if you want to calculate it, you can just do it by binary search. So if we want to, for example, calculate the height function exactly at this red dot, we would just start with the blue dot in the middle of the cylinder, and we would just we guess a few places using our membership oracle. And for each of these blue dots, we can actually see if the dot lies in the set or not. And so we can approximate where the boundary is on the line going from the little ball to the set there. This gives us a way to calculate this height function, which is the distance from this line to the border. So given this height function, let's turn everything a bit around and let's actually draw this. So this is again the line outside of the set with a point we want to query, and this is the border of the set. And now you can clearly see that this is just a function. And in fact, this is a convex function. So we're going to from now on assume that we have query access to this function. And what we would like to do is find some line that lies between the point and the graph of this function. Well, a very natural choice is actually just to pick a subgradient of this function. So here drawn in as a blue dotted line, subgradient always lies between always lies below the function, and it in particular also lies above the point if the point lies outside of the set. So our goal will be to calculate the subgradient, because the subgradient will actually separate the point from the function, and since the function is just the boundary of our set, it will actually separate it from the set. And classically, this subgradient can be estimated using O tilde n queries to the function. And this was already realized in the previous classical work, although how to do this was the complicated part there. But what we actually show is that you can get an exponential quantum query speedup for this. And this is the main takeaway. You can exponentially speed up this separation, this subgradient calculation, which gives you a separating hyperplane. So let me quickly say how you would want to possibly do such a thing, like exponentially speeding up a gradient calculation. And you use the algorithm which we already heard a bit about in the last talk by Jordan from 2004. So to recap this algorithm, I'm going to assume to start with that the function you want to take the gradient of is actually linear. So we have some function n, f from Rn to R that's linear, and we want the gradient. So as you normally do in quantum algorithms, you just start by setting up a superposition over everything you care about. So in this case, around 0, where we want the gradient, we're going to set up a grid of points in all directions, and we're going to build a giant superposition over all of these points. And then, as you do as a second step in quantum algorithms, you just query your oracle. So we query our oracle, but we're going to query our oracle in the phase. So we're going to add a phase e to the I f of x to every point denote x in a superposition. Okay, so, and now we're going to try and look a little bit differently at what we've just done, and we're going to actually use the linearity of our function here. So we're going to split up this f in f of 0 and the gradient transposed with x. Okay, so that's just rewriting, and we're going to just rewrite a bit more. We're going to split up this phase, and we're going to actually take out a global phase that corresponds to the value at 0. And we're going to write the summation over this grid as a summation over all different dimensions, where we now have, in the jth dimension, we have a phase corresponding to the jth entry of the gradient. Okay, well, we can just ignore the global phase, and we apply a quantum Fourier transform, or the inverse of the quantum Fourier transform, to be particular, on each coordinate. Because the realization that Jordan had was that this state here is actually just the image of a Fourier quantum Fourier transform when applied to the gradient of f at 0 in the jth coordinate. So what we just expect to get out is actually just a classical description of our gradient. So this is quite a neat algorithm, I think. It was early on discovered already by Jordan, and the nice thing is it exponentially speeds up gradient calculation over classical algorithms. However, there's a big if here. There's a linearity here, and our f, that will be the height function that I described earlier, is not linear, and in particular it doesn't even be smooth. It could very well be that there's a point in your boundary somewhere, and that's exactly where you want the gradient. So it could be that there is not even an actual gradient. The best you could do is give a subgradient. That's something that lies below the function, but is not particularly the gradient. Okay, how do we solve this? Well, the realization here is that f is, however, convex, because it's the boundary of a convex set, and it is Lipschitz. And it actually turns out, and that's the main technical lemma that we prove in the papers, is that this is enough to still calculate a subgradient. So this is a simplified version, and still requires quite a few lines, but suppose we have some function f that goes from a little box to R, and this function is convex and Lipschitz, then we can actually compute with probability 1 minus rho an approximate subgradient of f at 0 using only log n over rho quantum queries. So the main body of the paper is actually showing that this holds. And to do this, one of the things that we use is actually use a refinement of Jordan's algorithm that was given by Guyen, I can't pronounce this, sorry, Srini. Srini and Wiebe in 2017. They give a refined version of quantum gradient estimation. So I could advise you, if you ever want to do quantum gradient estimation, look at their paper. They have like 10 different versions for different situations. Sadly enough, convex functions that are Lipschitz was not particularly one of them, but we managed to make it work. So in total, let me recap what we did. We actually, from a convex set where we wanted a separating hyperplane, we built a function where it was enough to calculate the gradient of this function. And then you can use these techniques for convex Lipschitz functions to calculate this gradient. So returning to this diagram, what does that mean? It means that we can actually replace this order of n, which was the previous known classical bound, with a theta 1. So we have an exponential speed up there. And funny enough, this diagram is symmetric, and you can actually prove that this diagram is symmetric. So that also means that we can also put a theta 1 over here in the top right corner. So just to elaborate a bit more on what that means that if you have a validity oracle, which you can just think of as something that gives you the optimal value up to a binary search, then that's actually enough to also get an optimizing point when you're doing convex optimization. So if you have a great algorithm that allows you to calculate the optimal value, but you don't know how to actually get an optimizer out, then you can actually just directly use this and you can get the optimizer out. It should be said here, that, however, that we assume that all these things have logarithmic dependence on the error. So if you can only estimate the optimal value up to with poly dependence on the error, then this might introduce some extra cost. Okay, and what also is important here is that this diagram actually implies that you can also go from membership to optimization with only a linear number of queries. So previously, we had an n squared by just going from membership to separation to optimization in the classical case, but this actually is a quadratic improvement of the classical case by just using n queries. And it's not a quadratic improvement that relies on Grover, it's a different quadratic improvement for once. So there's still, however, a big open question. There's big O's here, which were actually thetas in the classical case, but we don't know in the quantum case. So can we actually just close all questions directly and stop with quantum convex optimization? Can we actually just make this tight as well, and then we're done? Sadly enough, not quite, but we have a few results on lower bounds here. So from considering lower bounds from separation to optimization, we can prove square root of n query lower bound via two different methods. So the CWI paper proves this from a reduction to search, and the Maryland paper proves this from a reduction to search with wildcards. But we both get the square root of n lower bound here. And then there's a slightly weirder lower bound, which is an n query lower bound. However, this has a very specific extra condition, mainly that the algorithm doesn't get this interior point in the set. This seems a bit weak because in the membership to separation case, we really needed this interior point in the set. But all the classical algorithms that reach this order n actually don't use an interior point in the set to go from separation to optimization. So it could very well be that the lower bound is actually, the bound is actually square root of n if you have a point in the set, but that would require a very different approach. It would require a quantum algorithm that uses this little point in the set where all the classical algorithms do not. So let me elaborate a bit on how you would prove such a square root of n lower bound. And I'm going to do this via the reduction of search, but to keep it slightly easy, I'm going to go from membership to optimization. So it's a slightly weaker lower bound. But the idea is mainly the same as the separation to optimization lower bound. So to prove a square root of n lower bound, we're actually going to do this from a search problem. So let x just be some binary string where we have to promise that there's only one 1 in x. So the Hamming weight of x is 1. And our goal here will be to actually find x, which is the same as just finding the one entry. So this is just doing a search on x. Okay. So we're going to define some convex set that hopefully will give us some lower bounds on this. And the convex set is the following. It looks a bit scary in notation, but all it is, it's always going to include the box -1 to 0 in each coordinate. but then there's going to be one coordinate in which we extend it. So in this image, the black line, this box is always going to be in there, but then we're going to extend it with one of the dotted boxes. And the question is, like, which one of the dotted boxes did we add? And the set has some nice properties. Mainly, we know a point in the interior of the set. Minus a half in every direction lies in the set with a radius of 1/3. So we actually have a point. That's a good start. And now we're going to look what happens if we're going to optimize just in the all ones direction. So we're going to move as much to the top right as possible. Now, if you would consider the case here down here where we have this dotted box added to the lower dotted box added, then optimizing as much as you can in the top right direction actually just puts you in this point, in the corner point of this dotted box. And well, what's this corner point of this dotted box? It's actually exactly the input x. This is always the case. So if we could optimize over the set somehow, then we could actually solve our search problem. But okay, so we still need to say how we're going to make membership queries to this. So remember, we want the lower bound from membership to optimization. So we know that optimizing over this set takes square root of n queries to x, but we want the lower bound not on queries to x, but on membership queries to this set. As it turns out, actually one membership query is exactly one query to x. And the way to see this is you can kind of partition the space into parts there that are never in the set. Everything outside and on top, the rest of the slide, basically. Things that are always in the set, this box. Well, both those types of queries are easy to answer. If somebody asks you, you already know that it's either going to be in the set or not. Or things that might be in the set because they're in one of these dotted boxes. And the things that might be in the set because of one of these dotted boxes, you can actually check whether such a point is in the set with just one membership query. If you want to know whether this point here is in the set, you only need to check the one coordinate of x. So one membership query is actually equivalent to one query to x. And this proves the lower bound. This shows that you're actually going to need square root of n membership queries to do optimization, because you need square root of n queries to x to do optimization. Okay, so here's a summary of all of the results together, and let me elaborate a bit more on what's all on the slide. So for upper bounds, we proved that you can get an exponential speed up from going to membership to sub. And also from validity, so calculating the value of an optimization problem, to also finding the optimizer. And this would also give a quadratic improvement from going to membership to opt. And on the lower bound side, sadly enough, not everything is tight. But we have a few different lower bounds, so we now know, or at least with a slightly more sophisticated argument than from the last slide, you can prove that from going from sep to opt, always is going to take square root of n queries. And we know that if you have this slightly weaker model where you don't know a point in the set, then actually you're going to need n queries. And this immediately also shows what the big open question is. It's closing this gap between these two situations. And we've tried, we haven't succeeded yet, so please solve it. And the main problem here seems to be to construct a set for which would give you a lower bound, for which you actually also know a point in the set. Because knowing a point in the set tends to make sure that if you have a lot of different possible convex set that could be the input, these are going to overlap a lot. Well, I think I'm going to leave it there. So thank you for your attention.
All right, I'd like to open the floor for questions.
Over there.
So you said that, at least for, well, right, at one point you said that this diagram is symmetric in some way. Does, right, the lowermost lower bound, so omega of n, yeah, with the asterisk, right? Does that tell you anything about the line above it?
So not fully. This diagram is symmetric in the case when you know a point.
Okay, I get it.
and in the sense that any algorithm from going from mem to sep will also give you an algorithm from fal to op, and the other way around, and from sep to opt as well. However, you might create a point in the set in particular. So it might be that all the problems of going from opt to sep always know a point, and then the lower bound without a point won't hold, because this particular instance in which it's hard is not included in going from opt to sep.
Hi. So when the function is differentiable, the subgradient just equals the gradient.
Yes.
So in your subgradient calculation, do you assume that the function is differentiable?
No. So let me go back to that slide. Here. So no, we only assume that it's convex and Lipschitz. So indeed, if the function is differentiable, it just gives you a gradient. But it doesn't need to be. It in general gives you something that lies below the function. So you could mention, for example, the function that's the absolute value function, which is just a sharp point. At 0, it would give you any linear function that lies below the absolute value at 0.
And are there good classical algorithms for calculating the subgradients of convex Lipschitz functions?
Well, in particularly the Lee-Sitford van Pala paper does this, and I think just the finite differences method would probably give you a good result, but you might need to do some smoothing or or step away slightly. So the Lee-Sitford van Pala paper, one of the things we also do is simplify the classical result. Because they assume an extra randomization step where you're not actually computing it around the point you want to query, or around the point that you know in the set, but you take a random step first to avoid some nastiness in the function. And so that might work. That works, and apart from that, you can also do some smoothing.
Thank you. I enjoyed your talk.
Thanks.
Okay. You were always connecting optimization oracles to member. I'm here.
Oh, there.
Yes.
Sorry.
Yeah, sure.
Sorry.
And in a sort of linear fashion, so you've got these 4 oracles, and you were connecting them only one to the one immediately to the right and to the left. Is there maybe a possibility of like this? Is there maybe a possibility of going in a direct way from membership to value oracle and vice versa, or something like that?
So the first thing to note is in the quantum case, it doesn't really matter because you can kind of contract these lines because membership and separation up to log factors are equivalent. And in the classical case, this is exactly an open question. So we know that the classical order n algorithm for sep to opt is tight, but the n squared from mem to opt might not be tight. It might very well be that that's linear. So it could very well be that classically mem to opt is indeed it's faster to go directly instead of going through sep.
You used a refined version of the gradient estimation. Mm-hmm. So what's the difference between this version and the original version by Jordan?
So the original version by Jordan really, it only considered linear functions or things that are very close to linear in the sense that it uses the second order Taylor expansion, and then you sort of have to hope that it doesn't matter too much if your quadratic term is big. And these things are worked out way more precisely in this refined version from 2017. In particular, they work out in a lot of cases what it means for your Taylor expansion not to be too big. So it shows that actually in these cases you are close to linear, and the Jordan thing will work.
Thank you.
Any further questions? All right, in that case, I have a question. I suspect it probably lies outside the convex set of reasonable questions to ask, so forgive me. But you were a co-author on the first talk as well.
Yes.
And these two talks seem to address at least superficially similar topics, quantum algorithms for convex optimization, and yet the talks, the content was, to me at least, very different. Can you hint at any sort of connections? How can I think of both of these talks or papers in the same way, or is that not possible?
I would find it very hard to think of them in the same way. And one of the main things is that the STP results particularly have a error dependence that's polynomial, because they use a lot of estimation techniques. So a lot of the results there are based on amplitude estimation-like results. And here we really want a logarithmic dependence on the error. And on top of that, we don't have any structure on the problem. That being said, if one of the things that you could actually link them is that if it turns out that this optimized step to opt is actually order n, this would give an improvement to STP solving. So in particular, this order n algorithm, which is an n to the power 3 time complexity, that's the best known right now, is the one that's responsible for the STP solver that was given in the first talk. So what I mean the STP solver, classical STP solver with logarithmic dependence on the error. So if you could improve that this line quantumly, then you actually get a really good speed up for STP solving as well. Even if you could just improve the n to the power 3 dependence in this, which is a computational task instead of the query task.
Cool, thank you. All right, last call for questions. In that case, let's thank all three of the speakers from this session.